So, afternoon everybody, great to see everyone. This is going to be just a bit of a quick talk on some forensic data acquisition, processing and analysis at scale. So, who am I? Currently in the IR space at KPMG, Cyber Response Services team. Previously, I was at WinSecure, F-Secure, WR, whatever they're called this week, in the content department, working as a threat hunter, nerd on all of the 2 and 3 letter acronyms, and yeah, in my spare time, I'm normally found up the hill with a brew, basically being a hobbit, which I admit to. So, what are we going to cover? So, cover some of the limitations of our current approach to digital forensics, what we've got to think about when we are trying to scale digital forensics, how we do it, some quick wins using a bit of science, and then a few case studies. Got a quick demo video for you at the end. So, let's just get cracking. So, how do we currently do small-scale incident response? So, if we're assuming that this is a walk-in, we've got no assets deployed, we don't know anything about the customer, so what we'll do, we'll either get them or we'll go on site or teach them how to get either a full disk image or a triage pack. So this is normally, we get the data, we get them to upload the data, depending on sort of where they are in the world and the sort of connections they have, that can be a massive problem. Then we get data downloaded to our analysis box. I live in the middle of nowhere, that's a problem. We'll run some stuff on the data that we get. So one of my favourites is Cape, Chainsaw, we can run Axiom, X-Waves, all the forensics tools that are out there. And then comes the really slow bit in that we select a single data point, we see if it passes the sniff test, and then we move on to the next data point. Repeat, essentially ad infinitum. So that's great for if you've got one box. If you're in like a police setting or a law enforcement setting, that's great. But there are some drawbacks with it. So, first drawback we'd say is effort scales linearly to the amount of evidence items you have. You have one host, it's going to take you a tenth of the time that 10 does. And also, if we have any changes in IOCs or attack TTPs during that analysis, we've got to go back to the boxes we've already looked at. We've also got limited disk space. If we've got a terabyte of disk image, that's great. If one box is 6 terabytes and we've got a disk image, where on earth are we going to put that? And also, when we are processing those images and those triage packs, everyone reviewing it normally has to download it to their own machine. Best case scenario, they're downloading process data. Worst case scenario, they're downloading the raw evidence data. This makes everything ridiculously slow. So, let's have a bit of change of mindset on this. If we sort of take what is roughly what we're going to be doing as part of that digital forensics workflow, so we're going to acquire the data, take the raw artifacts, make them into process ones, thinking like an MFP, for example, big binary. We store the data somewhere, and then we get analyst eyes on it somewhere. This is very simplistic, but if we think about this, then if I think of it from a data science point of view, well, we roughly map here onto extract, transform, and load. That is sort of the standard operating procedure for a lot of data science work. So when we start viewing it through that lens, we can start to have some really good possibilities. So we quickly go through what we do for each of those steps. So extract really depends on what data you have. So if you've got WAF logs, they might be in Cloud. If you've got a pop Windows DC, well, if you want a quick analysis, you might use some like Cape to get a triage pack. So for the initiated triage pack is essentially the files that are used forensically and none other fluff. If we get full disk image, that's where we'll get user files, we'll get Bob's desktop, we'll get everything. the thing that's really interesting about this is you can, in theory, scale any of these as long as you're willing to put in the code and the time. You could use PSExec to create a triage pack on every host in your environment. That's doable. But if you've got things like a disk image, great, you can get a disk image of every host in your environment. Where are you putting that? Therefore, you're probably best to use something like Velociraptor that is already built for that scale. So, for processing, we're going to use the Windows example. You're going to be probably throwing the Eric Zimmerman tools at it. And that's great. Again, you can scale that. You can use PSExec. But the problem is you're probably running out of Windows box. You can scale command lines, but scaling the Windows box, that's what's difficult. However, herein comes our secret sauce of how to scale. Most of the Eric Zimmerman tools now support .NET 9. .NET 9 can be cross-compiled with the Linux native environment. There are also some security tools such as Chainsaw, which is written in Rust, which is also natively cross-platform, so we can compile that into a Linux native environment as well. Most of the Zimmerman tools work as Linux binaries. From memory, the one that's really been annoying me is in PECMD, because it still requires a Windows binary to run. I will probably try to figure that out, but I haven't as of yet. So, and just to wrap this off, data load, we got to throw the data somewhere where it's useful. In terms of how we get that data, well, Logstash is a frequently used one. We use this at the start of this project just for familiarity reasons. We're now moving to Vector, which is a lot faster. And in terms of where we're getting the analyst eyes on it, we couldn't use OpenSearch because Amazon managed, and also we're familiar with it. Things like TimeSketch as well are really, really good. If anybody's got any experience in TimeSketch, I'd love to have a chat with you after, because it's something that I've, sort of semi-recently found that I'd love to take a bit more in. Oops. So, once you've got data into the platform, be that, OpenSearch, TimeSketch, whatever, we need to take that apart and derive useful findings from it. But here's where our scale problem comes in again. We've got loads of events, loads of different systems going into OpenSearch. That's brilliant. But then we still need somebody to look through it. And to get those useful findings, we can start to implement a detection system that will cut down the number of things we need to look at as analysts. The way that we choose to do it, there we go, is Sigma, which runs on top of Chainsaw, primarily for event logs. Again, really, really good, because we can throw that data into OpenSearch as well, and we can build lots of quick dashboards, which I appreciate the fact you probably won't be able to see, but we can look at all these pre-dashboards and get some really good info. But, once again, we have that scaling problem. If we get loads of detections going into OpenSearch, again, great, but we still got to look through it. Now, this phrase that you see here, data volume creates data context. This is something I talk about a lot when I'm trying to teach analysts about this stuff, and it's a phrase that I find is really, really useful. So come with me for a bit of a thought experiment. If we've got a host, we run a detection system on that host, well, the detection system will pick up false positives. It's just how it works. But those false positives will be from standard user operation, Windows stuff in the background, but also, admins doing admin things, whatever they want to do. But statistically, the false positives are significantly greater in number than the true positives, we hope. But if we scale that to 50 systems, well then those proportions keep going and keep getting higher. Say we've got a 99% false positive ratio, right? So if we've got all this data, theoretically, the abnormal detections, so statistically abnormal things, will be much more likely to be true positive, because if it's 99% false positive and we've got 15, 20 systems in there, well, the stuff that's only on one host out of 15 and is only like a couple of detections is going to be more likely to be true positive. For that example there, that's a real example. Of those, I literally just sorted by number of hosts. The only two that were false positive were these two. So those are high-level detections, they're not critical, and most of those top ones, which as you can see, Metasploit SMB, Mimikatz, not something you want to see. We can also exploit existing data relationships. So again, apologies, probably not easy to see it back. When you get a compromised user, that compromised user will sign in around the environment. They'll be generating 4624 type 3 events wherever they go. Well, if we have all 4624 type 3s, and we have the remote host they came from, we can just put it into a network graph and map where they've been on the environment. Again, anonymized but real example, we had a couple of users that we were tipped off that they were compromised. That would come from the client. So we just grabbed all the 4624s we could and found out exactly where they went, just by throwing into a graph. And also clients like the pretty graphs. Now, this example, a little bit more dev work, but still quite useful. So, this is something we did quite a lot when I was at Countercept. Here we have the detections coming to our own search cluster. So, what we would expect to see on a normal data set will be detection severity along the bottom, going in increasing severity, and we would expect to see that curve to be inversely proportional, which is sort of that sort of shape. However, whilst we see that sort of shape, detections go info, critical, low, high, medium, which doesn't work. Therefore, what we can do is go, okay, if we know that those relationships are skewed, data is more likely to be true positive, well, let's think about this as a machine learning problem. In the machine learning world, with classification, you require a labeled data set. Well, we could quite easily get a labeled data set, because if you look on GitHub, there's loads of ETX attack samples that we can run the same detection engine on as we run on known clean systems. Therefore, we can start to build that classifier. That was only 1,700 records. It's probably overfitting quite a bit, but this was like 2 or 3 hours of dev work. I'm sure if you get proper data scientists on it, you can then look, okay, which detections are statistically more likely to be true positive, irrespective of detection severity, right? Because that detection severity graph is unreliable for us. So, this is where a lot of the bulk of our effort is going to go. So, this is going to show you sort of roughly where we're at in terms of our own implementation, and I'm going to give you a bit of a walkthrough on some of the sort of detection logic and analysis logic that we can go through for this. So, this is roughly what the project was at inception. It's a lot more scalable than we were before. There's a bit of automation, but it's not great. It can handle quite easily when a client is throwing one triage pack at a time, and those in the IR space in the room will know that is quite common, especially if they're running around, grabbing stuff from air gap systems or whatever. So what we do, client will upload it to an S3 bucket. The analyst will then download the triage pack to their own machine and then point it and upload it again to our processing EC2 instance sitting in Amazon. That has the Eric Zimmerman tools, has Chainsaw on it. Can't lie, before we worked out that we could port .NET 9 to Linux, it was all running in Wine, which was exactly as janky as it sounds, but somehow it worked. We've got Chainsaw running, and we also have Logstash running on the same box, throwing the data into a managed Amazon OpenSearch cluster. For us, this is sort of tried and tested. It's actually still there. But just for ease of use, that's doable, right? We can just vary what goes into the S3 bucket because we're manually uploading it. So to just walk through what we had, this was one of the cases that used that particular system. We had 43 systems ingested, again, real compromise, 43 million documents. There was a DC in there, so it's not going to be 1 million each. That's probably averages out at that, but that's not reflective. 8 different data sources. We had MFT, Amcache, EVTX, and the EVTX nodes in the audience. 248 separate event channels were coming into that box. This was a ransomware incident, so we can assume we're getting some encrypted files. Again, appreciate those at the back probably can't see this. So what we did is we made a quick graph of NTFS record changes per extension. This, again, if we're thinking of data science terms, this is technically a velocity of NTFS record change. NTFS records can change when an extension is updated. So this is essentially a graph of velocity of extension change. Filter it for our suspect time period. Lo and behold, big spike with .black suit. So there's our malware. That's our ransomware variance right there. Next, all we do is go on the same MFT across all systems, look for anything with .black suit. Those are all our affected hosts. Again, relatively simple, but really good value. Next, search for any detection that's any way related to black suit. That first example is file.exe on Dave's desktop, which Sophos AV pulled out of black suit. Great. Then, we know file.exe. We can then pivot on Amcache to get evidence of execution across the environment for file.exe. This was on a completely different host than was detected in the Sophos example. Then we can pivot on sort of Dave's user directory, so desktop, downloads, documents, the whole shebang. We then found 2 additional files. One was an exe, one was a .sys. That was the EDR killer that they'd used because they got annoyed that Sophos kept detecting them. So we've gone from literally not knowing what malware variant was there to, hey, this is the file name. We can probably get file hashes out relatively easy if we have disks. We've got evidence of execution, and we've got their defensive aid in, 4 or 5 searches? So that's really quite useful for getting those findings rapidly, because again, as people in the IR space in the room will know, you don't have a lot of time normally. So, this is our sort of latest iteration. We've made pretty much everything changed. So, if we want to scale getting that initial triage pack, we can use Velociraptor. I know it's not really what Velociraptor was designed for, but for us this works. We can also still upload stuff manually. That works, and that's what I'll show you in the quick demo video on the next slide. That then goes to an S3. That S3, will then trigger an S3 event notification for the upload, and will trigger a Lambda function. That Lambda function will spin up an ECS cluster, so one container per triage pack that's uploaded. Then it will pull the file down from S3 and run all of our processing tools on it, so Chainsaw, EBTX, ECMD, whatever Zillion tools we want. It will then re-upload the data back up to S3, trigger a second S3 event notification, which will then spin up a second ECS for ingest. Now, that's solving a big problem that we had in the tools, especially EBTX, ECMD, especially Chainsaw, would use all of the resources it can get. Logstash also really wanted to use all of the resources it could get. So basically we had to keep trying to scale the box, and that became annoying. So we're splitting them out. We're also replacing Logstash with Vector. Again, pretty much sort of similar function, but it's also a lot faster. Not only is it a lot faster, we're going to spin up one per evidence item. So, JSON output from Amash processing, right? We're then going to throw it into an Amazon OpenSearch serverless instance, because the thing with serverless is that they'll spin up the capacity that you need for ingest. When we were stuck with Amazon Managed, it was right. Okay, we start the ingest, and then you just see the red line from the ingest instances in Amazon OpenSearch. So getting rid of having to manage those ourselves really helps with that. So next slide will be a quick video demo. We're concentrating on just the transform and load, because weirdly, no clients wanted me to test this quite experimental thing on their systems for some reason. So this is not going to be a test of Velociraptor, but this is going to be a test of the transform and load sessions. And I'll just get to the next slide, the video. Cool. So let's just trigger this. Okay, so S3 upload. We're then waiting to see whether the Lambda function triggers from that S3 notification. Give it a couple of seconds. Cool. So that is the S3 notification JSON coming in. It then triggers the processing ECS. I haven't cached everything properly for this demo, so it takes about a minute to kick off, but there are tricks you can do to sort of make that go a bit faster. That's spun up, and then here we have all the processing tools running after the download from S3 to the local ECS, and then throwing it back up. So, cool. Now we can see that all of the vector ECSs have spun up. Wait for them to get going. Cool. They are now processing all of the data, and they're going to be throwing up to OpenSearch. We let them do their thing. We can then move to OpenSearch, give it a couple of seconds for the ingest instances to do their thing, and we've got data coming in, and we hit that clock at about 4:45. This exact same example on the first iteration took about 10 minutes for data to start coming in. That's how starved for resources everything was. So we've got 18,000 events coming in within 4 minutes, 42 seconds, 52 seconds, and the rest came in probably about another 30 to 40 seconds later. So yes, it's expensive because you're spending loads of ECS, but frankly, it's Lambda and ECS. It's a lot less expensive than, a 60 gig EC2 sat there doing nothing for 90% of the time. So yeah, that's sort of some of my adventures in trying to scale incident response. Bye.